All right, let's jump straight into this explainer. We're going to tackle a really fundamental question about how data actually moves across a network. I mean, we talk a lot about switches and routers and cables, right? But what is the actual vehicle carrying your information from point A to point B on a local network? Let's find out.
Think about it for a second. If your computer just started blasting a raw stream of ones and zeros onto a network cable, it would be pure chaos. It's kind of like the classic postman problem. Imagine handing a letter carrier a folded-up piece of paper. No envelope, no stamps, no addresses. It's completely undeliverable. The postman has absolutely no way to know who it's for or who even sent it.
So, how do we fix this? Well, local networks use what we call a frame. A frame is essentially the network's version of an envelope. Before your computer sends any data whatsoever, it wraps that data in this highly structured package. It slaps a to address and a from address right on the outside. But here is the absolutely crucial rule to remember. This envelope is exclusively for local delivery. If your message needs to cross a router to get out to the internet, that router actually rips this envelope off entirely, reads the IP packet inside, and builds a brand new frame for the next leg of the journey. Okay, here's our roadmap for today. We've got 1, the network delivery envelope, 2, anatomy of a frame, 3, the lazy switch, 4, 3 types of delivery, and 5, the broadcast boundary. Let's dive in.
Part 1. The network delivery envelope. Let's start with the envelope itself and see why it's so critical for Layer 2 Ethernet communication.
Now, what's super interesting about these rules is that frames literally never travel end-to-end across the internet. They are strictly local hoppers. Think of IP packets as your ultimate cargo, traveling from your laptop all the way to a web server in another country. The frame? It's just the local delivery truck, getting that cargo to the edge of your building. Once it hits the router, the truck unloads, and the cargo gets put onto a brand new truck.
Moving on to Part 2, anatomy of a frame. Let's actually open up this envelope and dissect the specific fields that make the whole thing work.
Take a look at this. Every single Ethernet frame is built with these exact 6 fields, always in this exact same sequence. Whether you're sending a massive 4K video stream or just a tiny text message, this fundamental structure never, ever changes. So let's walk through what each of these building blocks actually does.
First up, we've got the preamble. This is basically just an automatic synchronization signal. It's 8 bytes of alternating ones and zeros that essentially shout to the receiving hardware, "Hey, wake up, data's coming, sync your clocks." And what's fascinating is that this gets stripped off by the hardware before the software even sees it. You're never going to spot this in a packet capture tool. It's purely a physical layer heads up.
Next up, we hit the destination and source MAC fields. These rely on a 48-bit hardware address that's burned right into your network card at the factory, and it acts as the ultimate to and from labeling system. The first half identifies the manufacturer, that's the OUI, and the second half is completely unique to your specific device. Interestingly enough, if the very first byte is an even number, it's a unicast address targeting one specific machine. If it's an odd number, it's a multicast or broadcast targeting a group. And to round out the frame, we have these final 3 fields. The ether type is kind of like a customs declaration. It tells the receiving computer exactly what protocol is packed inside the payload, like an IPv4 packet or maybe an ARP message. The payload itself, well, that's your actual data. And finally, the FCS, or frame check sequence. This is a mathematical wax seal, specifically a CRC32 checksum. The sender calculates a unique fingerprint of the frame and stamps it right on the end. The receiver then does the exact same math. If the fingerprints don't match up, the frame was corrupted in transit, and the receiver just silently throws it in the trash. No corrupted data ever moves up the chain.
Okay, Section 3, the lazy switch. This perfectly sets up our next point. How a network switch actually interacts with all these fields we just broke down.
So here's the crucial takeaway. Out of those 6 fields we just talked about, a network switch only cares about 2 of them. That's it. It reads the source MAC address to automatically learn the layout of the network, mapping that MAC to the port the frame just arrived on. Then it reads the destination MAC to figure out where to forward the data. It completely ignores the payload. It doesn't care if you're sending an urgent email, a database query, or a funny cat video. This deliberate laziness, this strict separation of responsibilities, is exactly why a modern switch can process millions of frames per second without breaking a sweat.
All right, Section 4, 3 types of delivery. Keep in mind a really important conceptual shift here. There aren't 3 different types of Ethernet frames. There's only one frame format. What actually changes is what we write into that destination MAC address field.
First up is Unicast. This is your standard targeted delivery. You put one specific MAC address in the destination field. The switch looks it up, finds the single port where that device lives, and forwards the envelope exactly there. PC4 gets it, and PC5 and PC6, they're completely oblivious. The conversation is totally private. This is your everyday web traffic, your file transfers, and your secure shell sessions.
But what if a device needs to find someone, and it has no clue what their address is? Say a new device joins the network and needs an IP address from a DHCP server, but has no idea where it is. It uses a broadcast. By filling the destination MAC with all Fs, FF, 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 it forces the switch into its flooding behavior. The switch copies that frame out of every single port. Everyone gets a copy. It's the network equivalent of grabbing a megaphone in a crowded room and yelling, "Hey, who has this IP address?" Then we have Multicast, which sits cleverly right in the middle. Instead of targeting one specific device, or absolutely everybody, the destination MAC is a special group address, which always starts with 01:. Only devices that have actively subscribed to that specific group will receive the frame. Unsubscribed devices never hear a peep. It's surgical precision, which makes it absolutely perfect for things like delivering an IPTV stream to 40 specific viewers without blasting it to the 60 people who aren't even watching.
So, to summarize the sheer elegance of Ethernet here, the frame structure itself never changes, not once. The switch's behavior simply adapts based entirely on what is written in that single destination MAC field. Specific MAC sends it to one port. All Fs floods it to every port. Group MAC sends it only to subscribed ports. It's an incredibly brilliant yet beautifully simple design that literally runs the entire world's local networks.
Which brings us to Section 5, the broadcast boundary. Let's see how all of this builds into network architecture, and specifically, the massive problem with broadcasts as networks grow larger.
Now, while a single flat network works beautifully for, say, 5 or 10 computers, scaling it up introduces a massive headache. Remember that broadcast megaphone we talked about? Well, if you have 500 devices on one switch, every single ARP request, every DHCP discovery, forces all 500 computers to stop whatever they're doing, open the envelope, read it, and discard it. It drags down performance across the board. If you've ever had to troubleshoot a sluggish network, this background noise is very often the culprit. And worse, there's zero security boundary. Someone in HR can easily intercept a broadcast that was meant for finance.
And that brings us to the absolute golden rule of Layer 2 boundaries. Switches? They'll happily extend a broadcast domain all day long. If you daisy chain 5 switches together, a broadcast frame just floods across all of them. But a physical router acts as a thick concrete wall. Broadcasts hit the router, and they stop dead in their tracks. Devices on broadcast domain B will never, ever see the noise from broadcast domain A. The router permanently terminates the broadcast domain. Which leaves us with a pretty massive architectural cliffhanger. If flat networks are noisy and insecure, but physical routers are incredibly expensive and wiring them up is super inflexible, how do we segment these broadcast domains logically? I mean, how do we carve up a single physical switch into secure, silent little micronetworks without spending an absolute fortune on new hardware? Well, that is exactly the problem that virtual LANs, or VLANs, were invented to solve. So looking at your own setup, how would you redesign your network?